the topic of network communication and all the different facets of a computer's ability to talk to another computer or a server over the network. Okay, and that starts with the physical layer. So that's where we'll begin with cabling and connectors. We have particular types of media that are going to be required in order to connect to a given network, Ethernet and twisted pair cabling being the most common, but we certainly have other options, older coaxial, newer fiber in certain situations, and even wireless. It's important that we understand all the different cables and connectors that can get used. Then it's also important for us to understand the protocols that are used, the languages that are used to communicate, which is largely going to be TCP/IP, but there are various application layer protocols as well that we need to discuss and how to identify those using port numbers. And then finally, in order to be able to communicate on a network, you need an IP address, along with some other configuration information. Every computer using TCP/IP is going to have this. Therefore, we need to understand how these IP addresses are constructed, how we utilize them to differentiate different parts of the address. We'll go through all of that in the IP addressing topic. In this first topic, we're going to be dealing with cabling and connectors. Okay? Physically connecting to a network is going to require a cable as well as a particular type of connector, and that's going to depend on the media that is being used. So we start with transmission methods, and data transmission is just the exchange of data among different computers between separate electronic devices. This can include both voice data as well as non-voice data. And network transmissions are going to include all different types of data in reality, okay? Different protocols and whatnot. Some transmissions are packaged as data files sent from source to destination, while others use more real-time or instantaneous transfer that's going to be supported through UDP. But the transmission types are going to vary, and that's going to be based on the protocol that's used, the applications that are interacting with one another, and just the general purpose of the network traffic. Let's do a quick comparison here between serial and parallel transmission. This is probably not testable, but just a little bit more historical. But the vast majority of network communications are going to be serial, where transmission occurs as a single clock cycle across a single medium. The bits are transferred one by one, with flow control as well as start and stop signals so that the systems know kind of where they're at in the particular communication. Your bytes, or 8 bits, are delineated either synchronously with time intervals or asynchronously using start-stop bit pattern. So WAN connections, Ethernet connections, all your network connections typically are using serial transmission. Parallel transmission is the transmission of data using multiple transmission lines. So we transmit an entire byte of data in a single clock cycle. These are not often used in networking, but they're used inside systems for data buses, printer ports, the SCSI bus, for data or hard drive access. That's where you would see parallel transmission. So again, not really overly relevant to networking. That's why we're not spending a bunch of time. But serial transmission is the predominant method in networking. We also have a distinction that needs to be made between baseband and broadband transmissions. Baseband means there is a single transmission line, and so signals are sent as a single transmission without the use of multiplexers. Only one signal can exist on the channel at any given time. We've alluded to this already with Ethernet. So all devices have access to the channel, but they can't use it simultaneously because there can only exist one signal. Only one signal can exist at any given time. Access methods then determine how the transmission channel gets used for multiple access. So with Ethernet, we said it was carrier sense multiple access collision detection. So they're all sensing whether the line is free, and if the line is free, then they go ahead and they try to send data. Broadband, on the other hand, uses analog signaling to send data over a transmission media using the entire bandwidth of the channel. The multiple signals, they can be combined using various frequencies, different frequencies, I should say, or channels. Broadband over power lines is a new technology aimed at delivering broadband capabilities using the existing power infrastructure. Things like cable, DSL, those are considered to be broadband types of technologies. So Internally in a LAN, we're dealing with baseband because we're dealing with Ethernet. Externally, using cable, DSL modems, the older T1 lines, etc., that organizations would use to connect to the internet, those are typically broadband. And another way of thinking about this is that, with a baseband, you can only tune in to one channel at one time, whereas broadband, often that term we think of cable, being able to tune in. There are multiple channels being used to send data over the wire. All right, media access control methods or data access, those are used as a set of rules to determine who can communicate on the network, how they communicate, and then also to define orderly procedures for that communication. This is not something that we get to pick. The choice of access control method is going to be determined by the type of network communication, the architecture that's being used, and they're loosely combined into two broad categories. Those are contention-based and deterministic. A contention-based is the most common. Deterministic is used by like token ring, where you have a single determining factor that determines who can actually send. In that case, it's the token. With Ethernet, it's contention-based. So in other words, we're all contending or fighting for the same bandwidth. And this concept of contention domains and broadcast domains is very important. Okay, within a single contention domain, also known as a collision domain, all the nodes are fighting for access to the same media. All right, so if the nodes transmit simultaneously, as we've discussed before, you will have a collision, and then there's a random back-off algorithm, and they sit and wait till they can try to send again. Now, this used to be a huge problem because we were using a physical device known as a hub. We'll talk more about network devices in the next chapter, but suffice to say that the hub is a physical layer device, which means it's really not capable of making any forwarding decisions. It can't segregate traffic. So when you plug a bunch of computers into a hub, it's one big collision domain. This is a problem because the more computers you have in a single collision domain, the more collisions you are inevitably going to have. There's nothing that you can do to stop that other than shortening the collision domain. Okay, so it was a problem if you had 10, 50, up to 100 computers. Now you would start to see the network slow down because behind the scenes there's a lot of collisions that are happening. Now switches and bridges for that matter, but switches and bridges operate at layer 2, so they actually can filter the traffic and only forward traffic that's necessary to a destination node. What they do, all switches will isolate collision domains to a single port. Now, you have the step to this was, okay, everybody was using a bunch of hubs, and now instead of a bunch of hubs, we'll say we're going to use 3 or 4 hubs. Client computers are connected to the hubs, and then the hubs are connected into a single port on the switch. That then becomes one single domain, collision domain, and you can have, say, 4 collision domains if you have a 4-port switch. That we've gone beyond that now, and hubs in modern networks typically do not exist because of this inability to filter and forward traffic. So most likely now the central device in an Ethernet physical star is going to be the switch. That means each individual node is connected to a single port in the switch, isolating these collision domains, and the switch is able to handle it so that people can actually communicate simultaneously. That has a huge effect on the overall performance of the network in a positive way. Now, there's another type of domain, though. It's called a broadcast domain. A broadcast is a network packet that goes out to everybody who's listening. And if a node sends a network broadcast, it's the broadcast domain that actually determines who gets that. Layer 1 and Layer 2 devices do not create separate broadcast domains. The only device that will create a separate broadcast domain is a Layer 3 device, which is typically a router or a Layer 3 switch. Okay, broadcast can slow down the network as well. So creating physical network segments, including routers, or by using routers, or Layer 3 switches, which, by the way, it's technically a router in the functionality that it provides. Doing that will have a positive effect on overall network traffic. All right, let's talk about data access methods. One concept we need to understand is multiplexing. This is a controlled type of access method that uses a centralized device to determine the time slices that a node will be provided. This is typically done on WAN wide area network links. We don't see this a lot internally. The signals are multiplexed by that central device across channels, and it uses one of typically three methods. Time division multiplexing is using discrete time slots where an individual node is given a time slot and they're given exclusive access to the medium for that period of time. Okay, simple enough. Frequency division multiplexing uses varied frequencies for sending multiple pieces of data across the same medium, where each sending and receiving node gets a unique frequency so they can communicate at the same time because they're technically not overlapping. And wavelength division multiplexing is sort of a more modern style of that frequency, or FDM. So those are just acronyms that you kind of want to know and understand the concept of multiplexing, just simply allowing multiple nodes to use a single line of cable using one of these methods. Digital signals, which is how computers are communicating, can't have a wide variety of values like analog. Digital signals are restricted to zeros and ones. Okay, so data is a series of zeros and ones, and it's just translated into a digital waveform. The waveform can switch between two voltage levels, 0 at the ground level and 1 at a positive or negative voltage state. These are very well suited for encoding data because the set values of every pulse in a digital signal represent a bit, and then 8 pulses represents a byte. Okay. Now, to be honest, this is way behind the scenes and not really something you have to worry about for Network Plus, but I think it's good to sometimes remind ourselves that literally everything in computing is digital, zeros and ones, on or off. And so the state of the data that is actually flowing across the wire is simply a series of zeros and ones in a digital waveform. In order to communicate, the very first thing that we need is a pathway to connect to each other. Wired network connections remain the most common type, although, of course, wireless methods do exist and have gained in popularity. There are a lot of different types of network wiring, and you can choose one depending on the scenario. Certain requirements like cost, speed, security, etc. Most Ethernet connections are going to utilize standard twisted pair cabling. While it's possible to see higher speed backbones use some form of fiber optic cabling. That's actually a statement that has, not necessarily stood the test of time. I mean, yes, you can still see fiber optic cabling, but we now have gigabit, 10 gigabit, and 40 gigabit Ethernet implementations. So it may not be required to use fiber optic cabling in every situation. Computers' connections to a switch, 99.9% of the time are going to be a straight Ethernet connection. Okay, switches to switches, routers to routers, forming backbones. That may involve, well, it certainly will involve at least higher speed Ethernet cabling or possibly fiber optic. So let's start with twisted pair cabling. Most networks will use what's called UTP, or unshielded twisted pair, to connect nodes on the network. Alternatively, we could be using a version of this called shielded twisted pair, or STP. And the difference is whether or not there is a metal shielding. So UTP is what we actually see in the graphic here. And yeah, there's a shield of a cable jacket, but that's not doing anything to prevent electromagnetic interference, otherwise known as crosstalk. So you've got 4 pairs of wires that are twisted around each other, and that twisting is done to reduce that crosstalk as well. Okay, these are then placed into an the ends of those cables are placed into an RJ45 connector, and then we can connect that directly into a port on a switch or the back of a patch panel, or we can connect it directly to the computer itself. Twisted pair comes in multiple categories. They vary in twist techniques. The goal is to minimize attenuation, or the loss or degradation of the signal over time, as well as to increase speed, all of which are available in both UTP or STP. A little bit more on STP. There's a metal shielding that helps to prevent that crosstalk, or EMI, from one cable to another. It is going to be more expensive, and therefore, for the most part, it's rarely used unless a situation specifically warrants it, because we've got a lot of interference. All of these categories, all twisted pair has a maximum cable length of 120 or 100 meters, or 328 feet. You will need to know that. That means that the signal can only be guaranteed for that length of cable. That does not mean that if you are at 110 meters, the cable will automatically not work, not function at all, but you'll start to see data loss. Okay, and so keep an eye on that if you are adding up the connections. And a connection is not, between me and the other computer. It's technically between me and the central computing device, the hub or the switch. So Cat3 was one of the originals, operated up to 10 megabits per second with 2.2 to 3 twists per foot. This is in the early stages of Ethernet. Cat5 was required for fast Ethernet, so up to 100 megabits per second, and that's got up to 20 twists per foot. Cat5e was required for gigabit Ethernet, operating up to 1 gigabit per second, about 20 twists per foot. Cat6 and Cat6a up to 10 gigs. Cat7, not really an IEEE standard, was never actually fully ratified. It uses a slightly different connector. Cat8 goes back to the RJ45 connector, which is the common one, and gives us 40 gig Ethernet, up to 40 gigs per second. So I would know the speeds. That's basically what we need to do. They all, except for Cat7, use the same RJ45 connector. They all have a maximum length of 100 meters. But they have different speed capabilities. And I should say internally, these cables are doing more than just the twist per foot. So Cat5e and beyond, they do add a little bit more shielding in UTP. The idea is the faster that you're sending data, the more power that's required to actually do that. And the more power, the more susceptible it's going to be to crosstalk. Now, there are multiple types of connectors for twisted pair, but as you see here, the vast majority of these are for phones. So RJ11, RJ14, RJ25, those are for phone connections, with the RJ11 being the current for everything. RJ45 is used for all Ethernet copper connections at this point. Okay, so 6P stands for 6 pins. 6 pins with 2 connected, 6 pins with 4 connected, 6 pins with 6 connected. With RJ45, you've got 8 pins because you've got 8 wires, 4 pairs, and each pair of wire is twisted around itself. But the connector is a little bit bigger because it's got 8 pins. There's a standard for wiring or creating cables called the EIA-TIA 568A standard. It defines the wiring patterns and the colors for twisted pair connections for residential. Version B is used for commercial applications. Now, that's really not that important. I mean, it doesn't mean one has to be used versus another. Okay, but basically, if you're going to use 568A on one end, you need to use 568A on the other end as well. If you cross the two, 568A on one side and 568B on the other side, that's actually called a crossover cable, and that can be required in some instances, but more modern networking equipment usually has the ability to do this translation on its own. So this would be important for you if you needed to make cables. Now, some of you might, when you get out into real world situations, you may very well be making cables. And so you would just follow this standard, matching up the color wires with the specific pins in the RJ45 plug, using a crimper to attach that and whatnot. So there are different kinds of cables. A straight through cable is a twisted pair where both ends use one of the wiring standards. If you have a computer that's connected to a hub or a switch, that's going to be you're going to use just a straight through cable. It's the same on both ends, and an RJ45 connector. A crossover cable is a twisted pair cable where one end is wired using A and the other is wired using B. This is used in cases where you need direct connections between maybe two computers. It's technically called an RJ48C. But you can make them yourself by just, again, using different standards on two ends of a cable. Now, I said in today's world, more modern devices are often able to handle this. Probably the most common place where you would see this would be between like a switch and a router, between a router and a firewall, using older networking equipment. A rollover cable is completely different. That's what's pictured at the bottom. This is a twisted pair cable that's used to connect to a computer serial port, or more likely, the console port of a router or a switch. Okay, and the ends are wired in the reverse of one another. So one end is using that RS-232 and typically a DB9 connector. So 9 pins, that's the old serial connector, whereas the other one is wired to Ethernet. I've got a couple of these in my bag because you will have to have them if you want to connect into a managed switch port or the console port of a router. We'll take a step back a few years here, just so that you know what this is. Coaxial cabling we usually recognize because of our cable TV, but this was actually used in older Ethernet implementations as well. The cable has a layer of braided wire or foil between the core and the outside insulating layers. You get a center conductor, and then you have that foil shield and braided shield. There's several different types of coax that are used, and the difference is the diameter of the core. I will tell you this is probably not that important to know all of these. They all had different uses. RG58 was the one that was predominantly used for networking. RG8, RG11, RG6, 59, those are used more for like I said, cable TVs and whatnot. A newer alternative is the twin axle alternative that actually has a pair of conductors in it. It's kind of hard to say where, if anywhere, that will actually pick up. Again, this is mainly a kind of a history lesson. In this demonstration, we're going to just take a look at some media types that we've been discussing, just to make sure you've got some good visuals. We'll try to have graphics and stuff, but occasionally we want to break off. We're not really doing anything in this demo, but we want to look at just other sources of information, if you will, and maybe some screenshots and whatnot. So I'm gonna pull up Google here, and we are going to look just for UTP cables. Okay, the UTP cables, and you can see we've got unshielded twisted pair. We've got good graphics. There's a good one. The difference between 5E, Cat 6, Cat 6A, you can actually visualize there a little bit more twist. Okay, here's a real good look of how the wires are twisted in and of themselves. There's a good look at STP, so you see that metal shielding that I was talking about. Again, just a graphic essentially, but just little things like that. Okay, so from the outside in, you're not going to be able to tell the difference between Cat 5E, STP, Cat 6, Cat 8, you're not going to be able to tell the difference. All right, you have to actually look inside the cable. Now, the vast majority of us will just buy cables, but then occasionally people will buy, 1,000 feet of 6A cable capable up to 10 gigabits. You can see that you can get 1,000 feet of cabling for $235. Well, if you do that, then we're going to have to create them. All right, let's just say make UTP cables, and you'll see the components. All right, this is a good. Actually, let's see. This is probably these are of course ads. Let me switch to images. Okay, so it shows the the wires and then how you would insert them. Here's your T568A and B standards. I mean, essentially all you're going to need is a cable stripper and cable crimper. Okay, and you can get a combo tool for that. And then, like, this is a YouTube video. I would suggest that you watch these. Some of these we're just not, with our setup, we're not capable of doing, but I would suggest you give it a look. You're not going to really be asked how to make cables on the exam, but you do need to recognize the standards that are there, okay? RJ45 plug. We've actually seen a couple of these. I guess that's all the same stuff, but I mean, that's basically what that's going to look like. Your RJ11 is going to be a slightly smaller phone cord that most of us have still seen. There's a comparison in the sizes between the RJ11 and the RJ45. Another one that's on the exam that's on the objectives, which I didn't talk about, is the F connector. The F connector is just a standard coaxial connector, okay? And I believe anyway, it's a standard coaxial connector. They have RG6 actually on the exam, and I believe that's because we don't use the old coaxial cables anymore. Nobody does. Nobody has for 20 years. So if you are dealing with a cable connection, it's probably likely to be attached to a cable modem, and RG6 is your most common type. But there are, the F connectors. That's kind of old style F connector. It could be called a barrel connector as well. They don't get into some of the older versions anymore. Let's go with twin axle. Okay, here's a twin axle type of connector. Again, more modern, essentially more modern cabling is going to do that. That's a really good look because you've just got multiple cores. That's why it's called a twin axle connector. Okay. So anyway, those are some of the things. Like I said, not really doing much in these demos, just kind of showing you around, but do that on your own. Go look at images, be able to distinguish between these. There are times when you are given a description of a connector on the exam, and there are going to be times when you are shown a picture, and you do need to be able to recognize them. Now, in addition to copper media, we have optical media, and that's fiber optic cabling. This is used for high-speed server connections sometimes, definitely for backbone segments. It carries light-based data through glass or plastic cores, and typically these are just a few microns, like up to 50 microns wide, and that means that they're actually no thicker than a human hair, okay? Because it's light-based data, not using electricity, it is very secure, very difficult to tap into, if not impossible, because you'd have to break the cable. And it's immune to EMI, completely immune. There is no such thing as crosstalk or interference with fiber optic because it's not an electrical signal. There are two broad categories, single mode fiber versus multi-mode. Single mode, as the name implies, carries one signal at a time. These typically, and there are different variants within that category, but these typically will be able to carry signals for much longer distances, all the way up to like 50 kilometers. Whereas multi-mode fiber carries multiple signals. They have a larger core and they use different methods, such as angling the light, as you see in that multi-mode in the graphic, or segmenting the core physically. They have various ways to carry multiple signals. But typically, because they're carrying multiple signals, there is a higher level of attenuation because at some point these signals could collide with one another. Okay, so typically multi-mode fiber is only going to be going up to 300 meters. There are a lot of different connection options for fiber optic cabling, but for all of them, it's more complex to join them than joining electrical wire because the ends have to be carefully cleaved and then spliced together. We have to make sure that the cores line up. So it's sort of a distinct skill is the word I'm looking for, a distinct skill and something that, typically if you're in networking, you don't do a lot with fiber optic unless you're in a field that deals with it. At that point, you would have had some serious training on how to physically deal with those. So this is more just kind of recognizing terms, recognizing different types of connectors and whatnot. So a ferrule is a cap that's placed over the end of an object to prevent splitting. And it has the purpose of terminating the end of the cable as well as easing the process of disconnecting from network devices. So fiber optic connectors are designed to connect and align the fiber cores so that light can pass through them easily. And you'll see these ferrules on a lot of these connectors that just make it easier to attach it to the actual server or network device. Let's talk about a few of these and we'll look at some others as well. ST, if you think of straight tip, that's the most popular connection type. In fact, you think of square top or stab and twist. It's got a ferrule on it that you basically just connect and then you turn to tighten. Standard connector, think of stick and click, okay? A 2.5 millimeter ferrule that snaps into the network device with a push-pull motion. So instead of turning, it's going to be stick and it'll latch in. LC is local connector. They're half the size of SC connectors. They also have a snap-in type ferrule, but you can think of little connector just because they're smaller. FC was an older one that's mostly been replaced by SC and LC connectors. And then probably the most likely one these days, well, that's not true. It depends on the type of fiber. But MTRJ, mechanical transfer register jack, those are duplex connectors. They have both fibers in a single ferrule, the send and receive, and they look like a mini RJ45 connector. All right, now in this demo, we're going to look at your optical cables and connectors, the fiber optics, and just get kind of an understanding here as to what we're dealing with. Again, this is going to be very similar to the last one, where we're just going to kind of look at some things so that you are able to make the distinctions. Okay, so fiber optic cable. If you look for that, you're just going to get some, pictures of actual cables. You can find graphics and whatnot that kind of describe exactly how that's going to work. I would suggest that we search for individual connector types, okay? So let's do that. We'll start with the local connector. Okay, that's a local connector, LC. If we bring this up a bit, we can see that, it's like the stick and click, SC, okay, but it's smaller. In fact, and this is probably for multi-mode, and then these would just be for standard single mode. So you got LC, FC, and SC. Let's search for all of them and see if we get a good image for the comparison. There we go. Oop, I was just trying to enlarge this a bit. Okay. So SC, stick and click, a locking mechanism, right? I'm not going to move my mouse because it'll stop zooming in. LC, the third one over there, is just smaller, but it's also that just kind of push it in and it will latch. You can see the little latching mechanisms on the top. ST over on the right, that's your ferrule. So you'll line it up and then you would spin that circular silver part to tighten it down. Okay, those are going to be your common types of connectors. Let's go back here and search for the MTRJ45. That's another, that's not it. Let's go back, MTRJ. There we go. Okay, so this is the MTRJ45. It looks like an RJ45 connector has actually got two different connections. And then you've got all those pluggables. Okay, so SFP, small form factor pluggable. Okay, that's actually SFP plus. When you start getting into the SFP versus SFP plus versus quad SFP, it's about really capabilities. Okay, so SFP, SFP plus is just going to be the plus is required to get up to 10 gigs per second. If you get into the QSFP, okay, we're going to see, let's see if we can get a good image or not here. Yeah, just different styles. The QSFP is up to 40 gigs per second. All right, and it's got quad connectors in there, which is why it's called that. But again, you can't really tell much of a difference. QSFP in a router should give you a shot here, maybe. Yeah, okay. So, I mean, basically, you've got ports that are either already on the routers or these are replaceable interfaces that can be plugged into a router, much like a PCI card can be plugged into a computer. So that's really all that's about, okay? Recognizing the different connectors, recognizing when they would be used, and as you go up in the connector type, we're dealing with the higher speeds of Ethernet. Sometimes we have networks that are running different media and we need to allow them to communicate with one another. Multi-mode to Ethernet, for instance, would extend an Ethernet network over a multi-mode fiber backbone. That's what we actually see there. So you've got the little MTRJ connectors and then the standard Ethernet connector. We've also got fiber to coaxial. You get single mode fiber to multi-mode fiber, okay, just in different areas if we needed to combine those, and then single mode fiber to Ethernet. I mean, this is pretty straightforward. A media converter is just going to be required if I'm trying to use two different types of cabling. We also have the concept of transceivers. I mean, we've discussed this, transmitter, receiver, but there are a number of different options here for network devices. This is routers, switches, possibly servers. Okay, so we've got a few graphics here, and you can just see it's basically, they call it a small form, or they call it a form factor pluggable, because it's basically just something you can slide in and it connects inside the server or inside the router. And it provides then an interface to connect fiber optic cabling. So we've got SFP on the top. You've got SFP plus, which actually isn't mentioned. You've got QSFP that has 4 connections, enhanced QSFP plus. This is, again, not something that you're really going to pick. It's just going to be based on the type of media that's being used and what is required. All right, but we need to be able to recognize those. These are just plug-in interfaces, typically to a router. We also need to take this time to talk about some of the connections outside of the organization's LAN. There are a number of different components that are required in order to connect the LAN to the ISP. The first one here is the DMARC, also known as the demarcation point. This is a terminating device. It's responsible for code and protocol versions as well as buffering. It is the device that then connects you to the ISP, and it's also the device, you can see based on that graphic on the bottom, it's the last device that's in the customer's responsibility. Okay. Now these have gone by different names. Network terminating interface, NTI, network terminating unit, network terminating device, minimum point of entry. They all mean the same thing. It's the demarcation point. And the demarcation point is connected to the network's main cross connect, which would be a switch that then allows access into the rest of the network. So especially older, well, still today, regardless, I suppose, anybody using T1, T3 type of lines, old ISDN lines, we would always have these demarcation points. They might be slightly different technology today, but it's still a point of interest. It's that last point that we have responsibility over. Let's talk about some of the other LAN components. This is just recognizing terms. These terms don't typically get used unless we're wiring buildings, but sometimes it can be helpful to know. Cross connect is just a location where signals are distributed to various destinations. If the DMARC and the main cross connect are different locations, a DMARC extension can be used, but usually the main cross connect is connected directly and in the same location as the demarcation point. The main cross connect is also called an MDF, or main distribution frame. It has a rack that has network devices that are used to manage connections between internal and external cabling. And then your intermediate cross connects are used in multi-story buildings, and that would be, having a backbone of multiple switches connected directly. All right. The workstation drop is the cable that runs from the individual horizontal cross connects, aka IDFs, or intermediate cross connects, I should say, and it runs out to each of the individual workstations. So we have an internet connection coming in. It terminates at the demarcation point. The demarcation point is connected to a main switch. That switch could be connected directly to other computers, or that switch could be connected with backbone cabling to other switches, which are then connected to the individual computers. Typical UTP installations for each floor from the horizontal cross connect are going to require a couple of different things. Multi-port hubs, or more than likely now switches, patch cables, the terminating block or patch panel, drop cables, and wall jacks. All right, so let's differentiate between all these. There's only one that may not make a ton of sense. The patch cable is the one from the wall jack out to the individual workstation. Behind the scenes, that wall jack is connected to a punch down block. The punch down block is essentially where you terminate those UTP connections. We'll see a picture of this. The front of the punch down block is going to have a port like an RJ45 port, and so it's the patch. The patch cable, is from that punch down block to the switch or the hub. Okay, so individual workstations are wired to a wall outlet, but behind the scenes, that wall outlet has to go back, be terminated a punch down block, have a patch cable to connect it to the switch, and then the switches are connected, out through the cross connects and DMARC and whatnot to get outside of the network. So patch cables are the cable that runs from the network card to the wall jack. The drop cable is the cable that runs from the back of the wall jack to the termination block found in the telco room. Telecommunications room is where the network wiring is terminated. Two different options. You got punch down termination with a cross connect, which is kind of what we see there, and then you have a patch panel. We'll take a look at a couple of these. The punch down blocks, the main component in the telecommunications room, which is used to terminate station cables, cross connect to other locations. The original was a 66 block. It originated with telephone cabling. Now we have a 110 block. It's used to hold wires in place using a molded plastic with horizontal strips. You can kind of, it's difficult to see with these images, but you see it on the back end, and then on the front end of the patch panel, we see what's there, just a bunch of ports. But on behind the scenes, behind that, you've actually had to terminate that connection so that you can then use a patch cable between that system and the switch. And the Krone or BICS are just different kinds of patch panels. We'll take a look at some images of those to help you differentiate. All right, now we've been talking about a number of different components that make up the local area network, and so I just want to kind of pull some of these up, see if we can get you a better view of it. Okay, this is actually what a demarcation point would look like in a wiring closet. Okay, so this is something that you'd be very similar to see, and so it sounds complicated, but it is simply your connection out to the ISP, okay? And it represents the termination of your responsibility. That's sort of like an older view or an older look, slightly older box maybe. Of course, this is a much older box, right? But I mean, that's all it is. In the wiring closet is your connection to the ISP. That is your demarcation point. Here's another view, a good one, okay? And you'll actually have things labeled typically to tell you, how you're getting out. And there's just a graphic. All right, let's look at some of these other ones though. Let's see, they punch down, and I know we had graphics in the lecture portion, but this is this is a punch down. So actually that's a great one. Let's see if we can just get that image without having to go to the... Okay. So this is a great one because it's a single plug, but it represents both, so you can see both sides. You can actually see the wiring schematic. This is how you would insert the wires from a single twisted pair cable. This is how you would insert the wires into the back end of that. And then you have an RJ45 jack on the front of it, okay? And so that's exactly what we're doing with some of these. It's just typically you're going to have a much larger view. And sorry, we don't want deals. I just want to actually see these. So this would be the back end, which is kind of hard to see, but then the front end. So that's your typical 48 port 110 patch panel. On the back, we have wires going directly in. They're terminated. On the front, it has an actual port number. That's where your patch cable goes and is going into a switch. All right. If we go back here and we search for the Krone block, you're going to see they're just different variants. Okay. So that's a Krone block, a slightly different variant, 200 pairs. Terminal block, strip wiring. It's going to have ports on the other side. No big deal. The other one was called a BICS. These are new ones. BICS block, just yet again, kind of a different style. All right, so you don't need to know the differences between those and whatnot. It's just a couple of different styles for the same concept, and that's a punch down block where the wires from the wall jacks are terminating. All right, so the most important part of that is probably just all the terminology. But like I said, I wanted you to actually see some of that LAN wiring, or the LAN wiring components, I should say, just to hopefully make it a little bit clearer. So we've been discussing the various physical connections that we have to have for a network. But in addition to that, we know that we have to have a protocol or a language that systems on the network will use to communicate with one another. And of course, there are a lot of different protocols, but a lot of protocols have a very particular purpose in what they do. And the underlying network protocol or protocol suite is pretty much consistent across all operating systems. This didn't always used to be the case, but now TCP/IP is the protocol suite that we all use in order to access to and from the internet and other systems. And then within TCP/IP, we have defined application layer protocols that allow us to perform very particular functions. So in this topic, we're going to learn all about that, and this is all very important, really in real life as well as the exam. So let's start with an overview of TCP/IP, which stands for Transmission Control Protocol Internet Protocol. This is a non-proprietary, meaning nobody owns it. It's an industry standard protocol suite, and it provides communications on networks with a goal of interoperability to support, various operating systems, hardware types, and whatnot. This was developed actually by the DoD way back in the 1960s. It is the foundation of the commercial internet. I mean, back in those days, 60s and 70s, the only networks there were really governmental, science related. And so you had ARPANET, which was a research network. You had NSFNet, which was the National Science Foundation network. You obviously had the government networks. TCP/IP became the protocol that provided the interoperability that we need so that we can use it on the internet, which now, obviously, with the internet, we are literally connected to nearly every spot on the globe. TCP/IP is not a single protocol. It's a group of protocols or a suite, and it's become the default for all major network operating systems. That includes, Unix, Linux, Macintosh, and Windows, because that's pretty much all there is these days. Okay, benefits of TCP/IP is it is routable, meaning it can be used on more than one network segment. That would obviously be key if we're talking about the internet, connecting systems across the globe. So it's completely routable. It defines essentially the addresses for a particular network segment, as well as the address for the host within that network segment, within its IP address, whether it's IP version 4 or IP version 6, fully routable globally. It's an open industry standard. That means it can be updated easily. It can be integrated into, virtually everything. Anything that can connect to a network is going to use TCP/IP. And it's very flexible in its packet headers, and it's got extensibility options for developers. Now, TCP/IP comes in a layered model, much like the OSI reference model, but TCP/IP chooses 4 layers instead of 7. And you might be thinking, well, how does that work? Well, essentially, it just means that the top layer, the application layer, handles protocols that fulfill the functionality of the top 3 layers in the OSI reference model. Okay, so application, what was that? Application, presentation, session layer. Those are all kind of bundled in. Their duties are bundled in the application layer. Transport to transport's a direct relation. The internet layer is just the TCP/IP name for the network layer in OSI reference. Network interface is a single layer that defines both data link and physical capabilities at the bottom of the protocol suite. So don't get hung up on the 4 layers versus 8. OSI reference model is the one that has the actual layers on the exam, just so you know. Okay, TCP/IP does not, but it's silly to jump into ports and application layer protocols without talking about the thing as a whole. Okay, so at the application layer, you have the protocols that will allow for programs to interface with the network. They'll perform a particular function like name resolution, remote connection, mail transfer, IP address assignment, etc. Transport layer are your 2 transport protocols. Every single network communication is going to use one or the other of these. All right, transmission control protocol, user datagram protocol. We're going to talk about these here shortly. And at the internet level, you have 4 core protocols. So transport and the internet, those are what we call the core TCP/IP protocols, the 6 core protocols in the suite. At the internet layer, IP is doing the most. ICMP basically assist, control message protocols, so it helps for troubleshooting. for IP. IGMP is for multicasting, and then Address Resolution Protocol, or ARP, is used to resolve MAC addresses to their corresponding IP addresses. And the network interface is really all about the media. Because the media, the Ethernet frames, the physical cables, the connectors, the things that we talked about, token ring and ATM are sort of antiquated technologies, but they would exist. Remember, TCP/IP is a protocol that can be used across multiple operating systems as well as multiple network architectures. So as we said, the protocol suite is made up of 6 core protocols. They reside at the transport and internet layers. TCP and UDP handle segmentation of packets, assigning port numbers to identify application layer protocols, and possible sequencing and error checking. The internet layer, IP, is the big one. It handles using IP addresses to route packets. It uses ARP to resolve the next hop. So that's the physical addresses, and then ICMP and IGMP just perform particular functions basically on behalf of IP. ICMP from a troubleshooting standpoint, IGMP for multicasting. So let's talk about the transport protocols in a little bit more detail first. There are a lot of functions that are performed in the transport layer by these 2 specific protocols, transmission control protocol and user datagram protocol, as we've mentioned. First function is fragmentation or segmentation, where you're dividing larger packets into smaller sections that are then made ready for transport. In any case, you will be assigning sequence numbers because the packets have to be correctly put back together at the destination. We briefly talked about this with the OSI reference model because, again, it's the same concept. They'll also use port numbers and sockets to identify application layer protocols. Basically, as the request comes down, remember, from the web browser, we have to have some way at the destination to identify that this request is for the web service, and so on and so forth, and vice versa, right? So the port numbers are going to identify the upper layer protocols. A socket is just an IP address and a port number combination. Okay, so it can use either of those to do that. That's the primary function of the transport protocol. Get it broken up into smaller sections so that it can be packaged for sending. Now, each of the 2 operate a little bit different. What we mentioned before was functionality that's consistent across both, but transmission control protocol is known as a connection-oriented protocol. Sometimes just referred to as reliable, but that means it's connection oriented. There's an actual connection made between the source and the destination computer prior to any data transfer happening. There is some communication there, basically an initial attempt to connection, an acknowledgement of that connection, and then a response, an acknowledgement of the acknowledgement. Okay, it's the 3-way TCP handshake is what it is referred to. TCP also provides sequencing, but also provides error checking. So part of that initial TCP handshake is you and I deciding how many packets I'm going to send you before you send me an acknowledgement that you received them. And that's the error checking. So let's say I'm supposed to send you 100 packets. I send you 100 packets and I stop and I wait. And if I don't get the acknowledgement, then I will resend the 100 packets because I don't have confirmation that you got them. All right. So that's where the reliability and the error comes in with that error checking. And that's the reason that TCP is actually used for most file transfers. Anything where we actually do need to know that you got all the data, we're going to be using UDP. Or excuse me, TCP, and like I said, it does use port numbers to identify those application layer protocols and services. Now, user datagram protocol is different in that instead of being connection oriented, it's connection-less, and therefore it doesn't support reliable communication. Basically, they call it a fire and forget protocol. Basically, I'm just throwing packets out there and I'm not waiting to hear if you got them. And if you didn't get them, I'm not going to resend them. Okay. Now, that's a little bit misleading because a lot of the applications themselves will have the ability to maybe resend packets. But that's the second bullet point there. Reliable delivery is basically the responsibility of the application. It's not inherent to the protocol. And the reason that they do it is to increase speed. Because if you're not sitting and waiting for acknowledgments as fast as all of this occurs, you're still going to speed it up. And so it's primarily used for streaming media as well as applications that would be dealing with, just very small amounts of data. Some application layer protocols will use TCP for some things and UDP for others. And DNS name resolution is a good example of that, where we need to make sure you got the information, a zone transfer. Well, that's TCP. When we just have clients trying to resolve names to IP addresses, that's a UDP type of query, because we're looking for increased communication speed. So TCP or UDP, key thing, and this is probably testable, is remembering that difference between connection-oriented and connection-less. Now, I briefly just described what a socket was, but here's a kind of a better look at it, just a graphical look, I guess. All network traffic is going to use either TCP or UDP, as we said, depending on the upper layer protocols. That's not a choice that we generally make. It's a choice that the application layer protocol will make. But the transport layer protocols use the concept of sockets so that when the information is passed up in the protocol stack at the destination, it'll be able to identify the appropriate service, right? If I'm sending an SMTP request, I want that to be routed to the SMTP service on a server. I don't want it routed to the web service, and vice versa. I'm trying a remote desktop connection to that system, and it thinks I'm trying to send it an email. That's not going to work. So we have to identify what's going on. So the application, or the transport layer is saying, okay, this information was passed to me from HTTP. HTTP uses port 80. Here's the IP address of this system, here's the port number. Those collectively are a socket. All right, and that's just really what the term means. Okay, now the internet layer is the next layer. Internet layer protocols are those that are in control of moving packets, getting them around the network, both internally within a LAN as well as externally on the internet. Internet layer protocols provide addressing and routing capabilities. And the network routing of packets is essentially just the transfer from one physical network segment to another. Okay. If you and I are connected to the same wireless access point or connected to the same switch, we can communicate directly, and we don't need a router involved. But anytime we are on a different network, physical network segment, it's going to have a different address, the address that identifies that segment. And anytime that's the case, I need a router, a network layer device, an internet layer device to be able to route packets. Your typical computer cannot just route packets out to the internet. The way that we get packets out to the internet is we don't know where they're going and we send them to our router. Okay, and our router may not know where they're going either, but it bounces from router to router to router using predefined paths called default routes until we get to routers that are actually knowledgeable of that particular network segment. So network routing is that concept. It's not just communicating from A to B, it's communicating from A to B across routers. And the routers are using these internet layer protocols to decide how to do that. So the core protocols, internet protocols, the busiest one, IP addresses, using those IP addresses to determine routing, delivering packets, all of those, and it uses the protocol addresses to do it. But it is a connectionless protocol, so it needs its counterpart on the side there, an internet control message protocol, to provide feedback for network communications. ICMP is also used by a lot of troubleshooting utilities. Ping, path ping, traceRT, we'll see some of these tools later on in the course if you're not familiar with them already, but they use different types of ICMP messages. But the ICMP protocol supports several types of messages that are really just used to help facilitate and help out IP, being that it's connectionless. IP uses address resolution protocol to resolve the MAC addresses for local network host. It then caches those MAC addresses in what's called the ARP cache, which is visible via the command line. And this is important, and we'll get into it a little bit more, but essentially, we're going to have two types of addresses in every packet. We have the ultimate source and the ultimate destination, which is an IP address, and those addresses can't change because that's how IP is making its routing decisions to get me from the source to the destination. But we also have to identify each individual hop. So my computer decided it didn't know where to send this, so it's going to send to the router. Well, the IP address is the ultimate destination. How do I identify the router, the next hop? That's always done using the MAC addresses, those physical addresses that are embedded onto your network interface card. So I'll get an IP address and I'll basically look at the ARP cache. Do I already have a mapping in there? If I don't, then ARP is used to essentially broadcast out and say, hey, who's got this MAC address? Or I'm sorry, whoever's using this IP address, give me your MAC address, and then we cache it. Internet Group Management Protocol is used for multicasting capabilities. It keeps tracks of the membership of a group that is associated with a multicast address. Remember, multicast is one to many, but it's only to those systems that have subscribed to receive this multicast, and IGMP is responsible for maintaining that. All right, at the internet layer, packets are referred to with a different name. If you ever see the word datagram, they're specifically talking about packets at the internet layer. And it begins to take on a nearly finished form that includes both the hardware and the protocol addresses, which are used to correctly route the packet. And I was just talking about this, but it gives you just a bit more of a visual. Source IP is always going to be my IP address. The destination IP is always going to be the ultimate destination. Let's say the web server out on the internet. Okay, those can't change, or else it would never get back to me. And so, the router is basically looking at those and saying, all right, is that destination IP mine? If it is, then this is the end of the line. If it's not, which in the vast majority of cases it's not, then I need to figure out where to send it. So it looks at routing tables and figures out how to send it. And each of those routes is going to identify, okay, here's the next hop. Here's the next router it needs to go to. And so your source and your destination MAC addresses are always switching at every hop along the way. And if I communicate with a web server, we already said I can sometimes take 15, 20 hops before I actually get to that server. Okay, source and destination MAC are going to flip every time. Just think of them as the next hop identifier, whereas the IP addresses are the ultimate source and the ultimate destination. The application layer in TCP/IP and the protocols that are there shouldn't be confused with actual software programs. Okay, so like Internet Explorer, Google Chrome, Microsoft Outlook, remote desktop connection, etc. Fill in the blank with whatever you want. That's not application layer stuff. Do those programs interface with the network? Yeah, they do, because those programs utilize an application layer protocol that exists in the application layer. Okay, so you can see the graphic there. They're all utilizing it, but they're just using it to interact with the network. So the application layer protocols themselves are those that we need to know that provide a particular function. It's important to identify what function it provides, so know what an acronym means and what the protocol does, as well as the default ports that are used. And this has always been a must for the exam. I'm not saying you're going to get 20 questions on it, but you'll get a few. And so memorizing this list is very useful for that. And certainly maybe not memorizing port numbers, although that can be helpful in real life. But definitely knowing the functionality provided by these protocols is a must in real life as a networking professional as well. The standard application protocols will use port numbers in the range of 1 to 1024. There aren't that many, don't worry. These are also known as the well-known ports. Okay, so where do we need the? Well, if we're opening up a port on a firewall, we would have to know this. If I'm connecting to a non-standard port on a web server, I would have to specify the port that I want to connect to. Those kinds of things. But a lot of it is firewalls and packet filters on routers, making sure we're allowing traffic, disallowing traffic we don't want, that kind of thing. So we're going to take a look at all these port numbers. Get ready. All right, so here are some of the well-known ports. This will be just something you have to come back to and some memorization. We don't have super easy ways to remember all of these. And the ones that we do, they're kind of silly. So well-known ports, HTTP. What we're going to do here is we'll talk about the protocol and exactly what it does, and I'll give you the port number because, again, I have to be able to identify both of those things. So the first there is HTTP, Hypertext Transfer Protocol, port 80 by default. This is the protocol that you use to transmit information on the internet, on the World Wide Web more specifically. Okay, from web servers to web browsers, HTTP is used to package up the data. HTTPS uses SSL, so that's the secure version of HTTP. You'll use HTTPS pretty much anytime you are entering any sort of personal information into a form, signing into a site, entering payment information. It would always be 443. FTP is the File Transfer Protocol. Now, this is as old as some of the other protocols on the list, I guess, 25, 30 years old. FTP doesn't get used nearly as much these days because we've got cloud storage solutions and all different ways of accessing. Sometimes behind the scenes when we're doing actual data copy, like downloading a file from a web server, you might be using FTP, but it's becoming more and more and more rare to actually use FTP clients to download things. But file transfer protocol, that's what it does. It transfers it. You technically have two ports, 21's coming in and 20's going back out for the actual data transfer. So it's still one that you want to know. SSH and Telnet are both remote command line administrative tools. Telnet is just plain text, an very old protocol, insecure on port 23. Typically that's disabled a lot of times these days. And SSH, secure shell, is the way to do it. SSH will work for both Windows machines as well as Unix and Linux machines. SMTP, port 25 is the primary, and there's actually a couple of additional client level ports. So port SMTP is to send mail to people. That's not what it actually stands for. Simple Mail Transfer Protocol, but I always remember send mail to people. And that's done on port 25. So your mail servers will be communicating email messages between systems on port 25. Clients connecting to SMTP can also use port 25, but sometimes we'll use ports 465 or port 587. Port 587 is the one that is not on the list there. DNS, domain name resolution, to resolve user-friendly names to numerical IP addresses to facilitate network communication. DHCP, dynamic host configuration protocol, to automatically assign IP addresses. We'll be talking more about DNS and DHCP later, setting them up and kind of what the different components are. RDP, Remote Desktop Protocol, that's the Microsoft method of remotely controlling both clients and servers if it's enabled. POP3 and IMAP4 are both older email protocols. And so they're older email protocols that are used to retrieve mail, generally from ISP servers, port 110, port 143 respectively. And then there are SSL versions of that as well. We'll do a quick objective check here at the end of this in kind of a demo form, and I'm also going to show you how to communicate with different ports on a system and how that works. So we'll look at those SSL ports, 993 and 995 respectively. TFTP, Trivial File Transfer Protocol, on port 69. This is actually was used for imaging and still is used for imaging for like network devices, like Cisco routers and switches, and then various other things. It's FTP uses TCP, whereas TFTP uses UDP is the primary difference there, as well as their use. SIP and RTP and H.323 and MGCP, those are all voice and audio video type protocols, and the different port numbers. So session initiation protocol initiates sessions between on voice over IP networks. RTP actually transfers the data. H.323 and MGCP are kind of like codecs, controlling compression and things like that. So don't have to get in detailed information about voice over IP unless you plan to kind of move your career path toward that. Here, just remembering those ports in case you see them. NTP, Network Time Protocol, at port 123. SMB is Server Message Block. That is used for accessing file shares on a Windows network between Windows clients and Windows servers. A very common protocol. that is used, not typically utilized out over the internet because a lot of ISPs block it just due to it's just got some vulnerabilities because it's used to actually get into data stores. SNMP is Simple Network Management Protocol. That's port 161. This is a protocol that can be used to gather information from network devices across the LAN as well as configure those devices. Kerberos is the authentication protocol in an Active Directory Windows network. So when computers are logging into their own system, they're actually sending Kerberos authentication requests out to the domain controllers. And the domain controllers are validating their account and then giving them a session token that they can use to access resources. And then NetBIOS is sort of an older Microsoft protocol, 137 to 139. You could see that called RPC as well, remote procedure calls. Just sort of a Windows client for networks built into that, but fairly antiquated at this point. So those are the well-known ports. We're going to do an objectives check in a demo where we talk about the different ports here just to make sure that we've got the full list. So as I said, nothing really I can tell you special here. You just got to memorize these. I mean, you're as I say, you're not going to see all of them, but you could see 3 or 4. You want those 3 or 4 to be easy, easy answers. So, and that's just going to take it a little time and a little bit of study. In this demonstration, we're going to take a look at the concept behind ports and sockets and application layer protocols. Now, a lot of times we don't really need to worry about this on a daily basis, right? We don't have to know a particular port that is being used unless we're trying to make sure that traffic is actually going to pass on a particular port. So it's that point, access control list, packet, that are a packet filter, firewalls. Those are the times where we need to know. We also need to know when something uses a non-standard port. Okay, for instance, a lot of firewalls, if you connect to them regularly, you won't be able to connect. However, if you use the non-standard port, that acts as like the interface to get into the public firewall. So it becomes important there as well. But first things first, let's try to just kind of understand the concept. So I'm going to open up Windows PowerShell here. And I am on Windows 11, just by the way, for these demos, so it looks a little bit different. This is the terminal in Windows 11. The way to get to this would just be, well, multiple ways, but you can just right-click the Windows key there and open up the terminal as an admin. And it looks like we're having a little mouse issues there. There we go. Okay, so Windows Terminal Admin is how I got to this. Now, there's a couple of utilities you can use to look at port numbers. Netstat-A would be one of them. Okay, that just shows this is your listening ports, but it's cool because you can see, okay, port 135, port 445, I'm listening on 3389. That's a remote desktop. It actually shows somebody connected. Okay, that's me. I'm connected to this machine via remote desktop. This is a virtual machine that's running in the Azure cloud. Okay. So, but my point is you can see the different port numbers, some of them standard, some of them not. I'll go ahead and hit cancel. Another way to see that is to go and look in Task Manager, just a way to get there. Task Manager, Performance, and then Open Resource Monitor. And on the Network tab, you'll be able to see the same thing, okay? Listening ports. And if anybody is connected, who is connected, okay? So again, it's just a way to identify, hey, these port numbers are actually being used. Let's do this. This is another good way. In PowerShell, you have a command called testnet connection. What I just did, by the way, was hit the tab key. In PowerShell, you can tab complete commands and parameters. So testnet connection, and then you would specify a particular computer name. And let's just do smtp.office365.com, okay, just as a test. Now, when you just do it that way, it will try to ping that system, all right? And so that, in this case, was successful. It shows me the remote address of that machine and that the ping succeeded. But what if I want to test on a particular port? Well, this is another way of doing this. You can see, will this allow me to connect in on port 25? And it does allow you to connect in on port 25. There's the TCP test is succeeded. Now, what if I choose port 80? Okay, well, that one worked also. So let's choose another port. Let's say 3389, like remote desktop. Okay. Now I'm going to sit here. It's going to wait for a response until it times out. And ultimately, it's going to tell me the TCP test failed, because that is an SMTP relay entry point for Office 365. Also apparently open for port 80. I guess I didn't realize that. But it's not going to allow RDP, remote desktop, and that's what 3389 is going to be. So it says that that failed, and then it'll go on and do the other checks. Now, the older way of doing this was Telnet. Testnet connection in PowerShell is just a little bit easier to use. Well, let's go ahead and cancel out of that. Okay. But I'll show you Telnet as well. So you're going to go telnet smtp.office365.com, and then you just go port 25. Okay. Now that's if it's actually installed. In this case, it's not. So we'll go install Windows feature. Well, it's not giving me those commands. So anyway, what this would have done was it would attempt to make a telnet connection into port 25, and you would actually get the response from that server. All right. So, but like I said, I mean, you can go here. Oops, that's the terminal. Go back to my browser here. I mean, typically when you go to a web page, you're not doing anything but just typing in the domain name. Okay. Now, when this switches to HTTPS, a secure connection, it's going to be using port 443. But otherwise, you don't really know the difference. Okay. And so, how would we go about specifying a different port? Well, here is the way, but before we do that, we're going to find a particular system to connect to here. All right, so we're going to go HTTPS, and this is a Cisco FortiGate firewall. All right, 2098 3.101. Actually, I'm sorry, I should do HTTPS, and this is FortiGate. And this is just a test firewall that I've got set up. Okay. And we'll go and look at that, and that's gonna kind of sit there, and it'll eventually time out. So let's do this. Let's make sure we can resolve that DNS name. Okay, it did actually resolve to the public IP, so that is correct, but it couldn't be reached. Okay, and here is an example where I need to specify a different port. So instead of using, and this is what a lot of firewalls will do, proxy servers, things like that, a lot of them will use 8008 or 8080. Regardless, it's a non-standard port number. You're not going to be asked to memorize this. It's just in order to connect to this web interface, you have to do that. And as soon as I do that, oh, look, here we go. I mean, yeah, I got a certificate error, but it's still taking me right to the front login page of the FortiGate firewall that's being hosted in Azure. Okay, so if you need to specify a port in a browser or in anything, it's colon and then the port number. All right, we're going to do a little bit of an objective check, and that's going to become a we did it at the end of the last chapter. Sometimes we'll do it in certain areas. Other times we'll do it at the end. CompTIA has a lot of stuff in their objectives, and I think this is just a good idea. So I also want to get you used to going back to the source here. All right, so this is exam objective 1.5, And it says that we need to explain common ports and protocols, their application, and encrypted alternatives. So basically, again, that means we need to know what these are. Okay, we need to know what they are doing. And we've talked about a number of these, but inevitably I'm going to have missed a couple. So we're in here just to see, okay, what do the objectives actually have? Let's go here. All right, so I don't think we mentioned secure FTP, which is basically file transfer protocol using secure shell, which is why it has the same port of 22. Okay, we mentioned these other ones. NTP, IMAP, I believe we've got all that. LDAP, just in case. I didn't mention that's 3389. That's communication with domain controllers or any machine that's running a directory services, which is like Active Directory. We've got HTTP with SSL, HTTP with TLS, both HTTPS, both 443. SMB, we mentioned. Syslog, I did not mention that one, so that's 514. Syslog is a mechanism that can be used to collect event logs from multiple network devices, whether they're running Windows, Linux, Cisco IOS, doesn't matter. Pull them into a central location. 587, we'd mentioned that. They've got it listed as SMTP with TLS. SMTP is typically always going to be protected with TLS. It's definitely going to be protected with TLS encryption when we're talking about client connections, and that's what 587 is for. Secure LDAP, I did not mention, that's 636. So 389 for regular LDAP, encrypted LDAP is 636. For IMAP, I believe we mentioned this but didn't have it on there. So IMAP is 110. I can't find the other one now. 110 or 993 with SSL. Excuse me, 143 or 993. POP3 is 110 or 995. Just remember those two. With or without SSL just means with or without encryption. So these protocols typically don't inherently have any security, with a couple of exceptions like SSH and SFTP, right? Most of them are unsecure. And so they're going to use SSL or TLS to secure it. SQL, I didn't mention, that's port 1433. And you've got a couple different variants, SQLnet 1521, MySQL 3306. Those are just, again, variants to different kinds of SQL databases. RDP we mentioned, SIP we mentioned. Okay, and then we've talked about these. A couple here that we haven't mentioned, but that's IPsec stuff, and we'll be dealing with that in the security section. So again, just a quick objectives check. I want to make sure, I highly recommend that you go download these, that you be able to look at this and not only know what that protocol does, but what port number it's going to utilize. I will show you one other area here. Okay, and that's, if I am going to add a program through, add an app or feature through the Defender firewall, I mean, they'll let you just click this, but if you click allow another app, we can browse to it and locate that, or we can go to advanced settings, and personally, I'm always in here. And when we go to creating new inbound rules, notice we can define just by port number. Okay, so I get TCP or UDP. These are the port numbers that I would like to allow. Okay, I want to allow the connection or I want to block the connection. I want to apply it in this network profile. We'll talk more about the firewall later, but that's a place where we would see those port numbers. Okay, firewalls, routers, those are the typical places where the port numbers come in play because they're allowing or disallowing traffic based on what port number, because that actually identifies the type of traffic that it is. All right, so that's going to complete our demonstration. We wanted to look at ports and protocols in comparison so that we understand them, but then also kind of compare what we talked about to the objectives to make sure that we've got all of those. Those are going to be very important from a memorization standpoint. In this next topic, we're going to look at IP addressing. We've discussed the fact that TCP/IP uses IP addresses to assign to all hosts on the network to uniquely identify them. But we need to understand as networking professionals what these IP addresses look like, how they're made up, how routers use them to make decisions, how computers use them to make decisions, and how we can troubleshoot when IP address configuration goes wrong. And that's really what we're going to be discussing in this topic. So let's start with an introduction to IP addresses. The current version of TCP/IP that we're still heavily using is known as IPv4. And it specifies a particular address structure using 32-bit binary addresses. Okay, now these are IP, Internet Protocol addresses. So they are the layer 3 protocol addresses that get assigned either manually or automatically to a network interface card. And they are required. In order to communicate on a TCP/IP network, you have to have an IP address. And that IP address has to be configured properly, because it's a logical way of identifying you. Okay, much like just a street address would be necessary for any communication via the United States Postal System, right? So the IP addresses are numeric. They're 32-bit binary numbers, but they're written in a decimal form and grouped into octets, which are 8 bits. In the format there you see of, w.x.y.z. That just means it's 4 groups of 8, making it 32 bits. In the IP address, a part or a portion of the address is going to belong to the network segment, and the other portion is going to belong to the host. We call those network ID and host ID. So everybody on the same network segment shares the same network ID, but they all have unique host IDs. Okay? If you have multiple network segments, each network segment will have a unique network ID, but then can use the same host IDs within that network ID. Think of it as a street and a house number. Everybody on my street lives on Oak Street. Nobody else lives at 123 Oak Street. However, Maple Street, which is right next to us, has a house that's 123. That's okay, right? Yes, because of the distinction between the street name and the house number. All right. I use that as an analogy here. We distinguish between the network ID, which is the same for all systems on that particular network, and the host ID, which is unique within that particular network ID. So the configuration that you need on a TCP/IP network is an IP address, but along with an IP address also comes a subnet mask. And the subnet mask is another 32-bit number, and it's used by routers as well as hosts to determine the network and host portions of the address, to differentiate between the two. Okay, so how does this go about doing this? Well, subnet mask is 32-bit binary as well, but the subnet mask has slightly different rules than the IP address. In the subnet mask, you have continuous binary 1s followed by continuous binary 0s. You can't have you can't mix and match. Okay, so it can't be like 1 0 0 1 1 1 1. It would be all 1s. When the 1s stop, the 0s start. That's also your dividing line. That's the line that differentiates the network portion, everything to the left of it in the address, versus the host portion, everything to the right of it in the address. And to illustrate that, we've got some stuff highlighted here. First one on the left, 192.168.1.200, that's a 32-bit IP address. Okay. The next one, 255.255.255.0, that's a subnet mask. Well, without going into the binary, which we will when we get into some of these demos, but without going into the binary, I will just tell you that all binary zeros is 0. 8 binary zeros is 0. 8 binary 1s equals 255. Okay, and you can go through the conversion and figure that out. So basically what we have is contiguous 1s in octet number 1, 2, and 3. So that is the subnet mask acts as a mask for the portion of the address that's the network portion. Okay, that's another way of saying it. The mask is on; it's all 1s. So whatever portion of the address that corresponds to is the network ID. Once the mask turns off, the rest of it is the host ID. So in this case, the first one there, the network ID would be 192.168.1, and then you just say .0. Because you're not using that 4th octet, and the host ID would just be 200. Over on the right, 172.16.18.128, but the mask is 255.255.0.0. And so it's now only on for the first 2 octets of the IP address. Therefore, the network ID is 172.16. Now the mask is done, so we'll just put 0 zeros in the host portion. Right? So 18.128 was the actual host ID. And this is the kind of it's pretty basic stuff. We have to be able to recognize this. I have to be able to look at an IP address and tell you what its network ID is versus what its host ID is. And I do that solely based on the subnet mask. All right, so that's a quick kind of overview. Don't worry, we're not leaving you there. This is a complex subject that a lot of people have struggle with until it finally clicks, and when it does, you'll get it. So let's talk about some address rules. There are rules that apply to IP addresses as well as subnet masks. First off, in 8 bits, the maximum value that you can get is 255. The lowest value you can get is 0. Okay, so we're not going to have any negative numbers. Can't say I've ever seen that as an option on a test, but we're not going to have any negative numbers. We're also not going to have any numbers over 255. So 172.16.0.254, that's a valid address. 172.256.244.100 is invalid. Why? The second octet is 256. Anytime you ever see a number over 255, it's incorrect. The host portion of an address can't be all ones and can't be all zeros. Now this one gets a little bit tricky as you're kind of thinking about it. You're like, what? Well, we write the network ID with all zeros in the host portion. Okay, so if my network ID is 172.16.0.0, that's how I write it. That can't also be an IP address. The network ID takes the all zeros in the host portion, and then the network broadcast address takes the all ones. So, you know, again, they're 10, just assume it's just the first octet. 10.0.0.0, that's invalid. 10.0.0.1, that's valid. 172.16, if it's divided in 2 with 255.255, that's invalid because that would be all ones in the host portion, and that is actually the network, the subnet broadcast address. And then the final one is the host and network combination needs to be unique. So you can have 2 systems on 2 different networks and their host ID for both of them is 100, and that doesn't matter because they're unique within their own network segment. You cannot have 2 machines on the same network trying to use the exact same IP address. The subnet mask has a different rule, and it's because in the subnet mask, the binary numbers, it's 1 or 0, but the ones have to be contiguous and the zeros have to be contiguous. They can't start and stop. So therefore, there are only certain valid values for a subnet mask, whereas in an IP address, it can be anything between 0 and 255, generally. In a subnet mask, there are only, 9 possible choices. All right. The one choice that's not on there is, of course, all zeros. 128 is just the first one. 192, 224. You can see how the number of ones are increasing. 240, 248, 252, 54, and 55. Those are the possible subnet mask values and their binary equivalent. That may not seem like it matters, and in many cases it doesn't. When the subnet masks stop with the decimal points in the IP address, it makes it much easier because all you're ever dealing with is 255. But if you have a subnet mask like 255.255.224.0, well, then at that point, somebody has taken the time to create and manipulate to try to create additional subnets that we can assign to router interfaces. And so we have to actually then figure out, okay, what is the actual network ID? Because it's not blatantly obvious, and we're going to have to convert into binary. But right now, the main thing is the rule here is contiguous ones. They can't start and stop, so you can't just have whatever value you want in a subnet mask. The 3 components that usually get given out by DHCP are going to be an IP address, a subnet mask, and a default gateway. The default gateway is just as important as the IP address because it represents my way off my local network segment. Computers only know how to communicate directly with machines in their own local area network. They're not going to have information about how to get to Google, to Microsoft, to Yahoo, to CNN, to whatever, fill in the blank. I'm not going to have any of that information. So a client basically knows this is the network I'm connected to. If another machine's address is in that same network, I'll communicate with them directly. If the other machine's IP address is not within my network, then I will communicate to my default gateway. That's it. So the default gateway is the route out to the internet. It doesn't mean it's got a public address. I mean, it's on the network segment, but it's the other host way off of the network segment. So you can probably think about how critical this would be. If a default gateway is missing, you can't connect to the internet, but can communicate internally. If a default gateway is configured incorrectly, same deal. You can communicate internally, but not out to the internet. Default gateway, its configuration, and then the actual device that you're pointing to, those are one of the first places to look if you're trying to troubleshoot access outside of the local network. All right, in this demonstration, we're going to take a look at just working with binary IP addresses, understanding how subnet masks work, and how subnet masks are used to differentiate between the network portion of an address and the host portion of an address, okay? Now, this is not going to be anything fancy. I've just got Notepad opened up. You can use Excel or something if you want, but this is, it's just an extremely important concept for us to get down. All right, so first things first, we're going to draw out our binary digits. And remember from the first chapter how we talked about the numbering systems, and that in binary, at least with IP addresses, we're always dealing with 8-bit numbers, okay? And it's a 2-base numbering scheme. So we have something like this. Now, when you do the test, if you do it in person, you will get a scratch piece of paper. Even if you do it online, you can still have a piece of paper. This is a good idea to definitely write down. It will allow you to quickly convert numbers from binary to decimal, okay? Now the slots here aren't going to be exact, but you'll get the idea. So I'm just going to put in a random 8-bit number. Okay, and we're going to then convert that 8-bit number into decimal. These are the values, okay? This is the actual 8-bit binary number. FYI, if you ever see a number that's not a full 8 bits, then always assume there are leading zeros. So if they give you a number like 1100, you know that there's 4 zeros at the start of that, okay? We have to assume that, otherwise it doesn't work. In order to convert from binary to decimal, we just count the values that have a binary 1, okay? So we're going to add 128 plus, we're going to count the 64-bit. We're not going to count the 32-bit, but I'll put a 0 there just for clarity. We're not going to count the 16-bit because those are both zeros. We're going to count the 8-bit. We're not going to count the 4-bit. I'm a little offline here. We are going to count the 2-bit, and then we're not going to count the 1-bit, okay? So then basically we just add up those numbers. So 128 plus 64 is going to be 192, plus 8 is 200. So this number, this binary number, represents the decimal number 202. Okay, now I'm going to also open up the calculator. You're obviously not going to have the calculator, well, maybe not obvious, but you're not going to have the calculator on for the exam. However, this is a good way of checking yourself, okay? So if we go into, let's see, actually, I think they changed this on us. Yeah, there it is. Into programmer mode. And then we say we want a binary number, and the binary number is 1100. 1010, okay, that's that number right there, and then we automatically see that in decimal that's 202. Okay, so that's just a quick check, but all you're doing, the 1 just means you count that corresponding value. So you count that value. If it's a 0, you don't count that value. If we were to go the other way, okay, let's say we have the address 192, or we have the number 192, then we're going to start from the left, and we're just going to say, okay, can we take 128 out of 192 and still get a positive number? Can you subtract 128 from 192 and still get a positive number? And the answer is yes. Okay, so then you would go ahead and put a 1 there, subtract 128, and that's going to be equal, now I have 64. Okay, obviously 64, then that's a 1. Well, Now I'm at 0. 64 minus 64 is going to be 0. So now the rest of these are going to be zeros. Okay? And that binary number 192 is 11000000. All right, so that's the conversion from decimal into binary and binary into decimal, and we do need to be able to do that. So now that we have that, we're going to move on to taking a look at IP address and subnet mask. Okay, so I'm going to go 192.168.1.200 with a subnet mask of 255.255.0. All right, now what we're basically saying is, and if it helps to, I'm going to convert this subnet mask into binary, and this is going to be pretty easy. Okay, 1 1, it's 4 ones, a period, or excuse me, 8 ones. I'm spreading it out just so you can kind of see it, but I mean, I guess that actually may make it a little bit harder, so let's just back these up. 255.255.255.0 looks like this in binary. All right. And so I think looking at it like that kind of helps to illustrate this idea of this is a what? This is a mask. This is the subnet mask. And so when the mask is on, in other words, the values are set to 1, then that portion of the IP address that it is blocking represents the network portion. I'm going to keep this in decimal, okay, because we don't really need to convert those numbers from decimal because it's the entire octet. It's saying the entire octet is a part of the network ID. Another way of saying it is when the ones stop, you can kind of draw a line, and everything to the left of that line in the IP address represents the network ID. Everything to the right of that line in the IP address is going to represent the host ID. Well, when I'm writing the network ID, I'm going to just write it as 0. So all zeros in the host portion, that's why we can't use that as an IP address because it represents the network ID. Okay, so I mean, in the case of standard subnet mask, it's, I don't want to say simple. I realize this is a stretch of our minds, but it is going to be that straightforward because, and you don't actually, and by that I just mean you don't have to convert from binary into decimal or vice versa, right? If it's 255, if it's blocking the first 3 octets, then we know that the first 3 octets are the network portion. That means that 200 is actually a host ID within that network segment. So if I'm writing the network ID, I'm writing it as all zeros in that portion, 192.168.1.200. Okay, let's try a different one. Let's say it's 172.31.100.10 and a subnet mask of 255.255.0.0. Same deal, right? Here we've got the mask on for the first 2 octets. We draw our line at that decimal point. Everything to the left is the network ID. Everything to the right is the host ID. So if I were to write the network ID, I would write it as 172.31.0.0. All right. This is actually the process that a computer goes through when it's trying to communicate with a remote IP address, any IP address. The very first thing it does is to determine if that IP address is on the same network as itself. Okay, if it is, it just tries to communicate directly with that IP address. If it is not, it will communicate with its router, its default gateway. Now, how is that actually done? Well, it's actually done by converting these into binary. So let's make this easier here. On decimal, we'll say 172. Again, you can just look at what it is in binary. So I'm going to convert, I'm going to convert that 1010. Okay, that's 172, and actually I'm just going to do it this way. Whoops. Okay, so 1010.1100 is 172. All right, we're going to take this whole IP address, actually, 10. Okay, so now we need 31. Well, we know we can't count the 28, the 64, or the 32 bits because that would already be too much. And here's a little trick. Anytime your number is right under one of these, it's going to mean it's zeros up to that point and then just ones the rest of the way. Now, you can certainly test it, but 16 plus 8 plus 4 plus 2 plus 1 is going to be 31. All right. So so far, this is my IP address, 172.31. Now I need 100. Okay, so that's going to be 0 plus the 64-bit plus the 32-bit gets me to 96. So we're going to have 0 at the 16, 0 at the 8, 1 at the 4. That gets me to my 100, and then 0, 0. Okay? And then the last one is 10, so we're going to have a lot of zeros. 4 of them gets me to the 8-bit. I can count the 8-bit plus the 2-bit, and that would get me 10. All right? So that's the IP address. And here's the subnet mask. Okay, it's 16 ones followed by 16 zeros. Now, what is actually happening at the computer level is a process known as ANDing. ANDing is combining two binary numbers. The only way that the result is a 1 is if both values are a 1. Okay, and we're talking about IP address combined with subnet mask. You're not adding. I suppose you could say you're multiplying because anything times 0 is going to be 0. All right, but it's really just, okay, are both values, if it's like a Google search where you search for term A and term B. I only am going to see the results if both of those are true. All right, so let's follow that logic though. So the first one there, they're both 1, so that would be a 1. The second one, 1 is a 0. Okay, now we have two 1s. We have a 0. We have 1, 1. Top ones are zeros. Okay, now we're on to the next one. Now, you might already notice something. Wait a minute, that number is exactly the same as that number, right? And it always will be. When the mask is 1s, it has to match because the only way the value would be a 0 is if the top one was a 0. So this is just illustrating the point, but doing it in binary. And now once the mask is 0, well, now the rest of them have to be zeros, right? Because you can't possibly have it. What does that equal? That equals the network ID. So that's what the system, I'm not saying you have to do it that way. When it stops on the decimal points, it would be silly to convert it into binary and do it that way. I'm just trying to illustrate the idea. That's what the computer system is doing. And it's then evaluating, okay, that's the network ID. Well, that is 172.31.0.0. All right, so if I were to convert it back into decimal, that's what it would look like. Okay, so that's the way a subnet mask differentiates between the network ID and the host ID. And again, if it's like this, that's easy to figure out, right? I mean, it's just hiding the first octet. Just start thinking in octets, the groups of 8 bits. It's hiding the entire first octet. So the network ID is 10.0.0.0. The rest of this represents an individual IP address within that 10 dot network. All right. And most of the time, you'll see them stopping like that. And most of the time, especially if the network designers and architects are, thinking to try to simplify, we're using private IP addresses, which we'll talk about in a minute. So we have a lot of flexibility. And so we have decimal-oriented brains, and we should just leave the subnet mask stopping on the decimal points. However, having said that, on both the test and in real life, we might run into something like this. 172.16, let's say, .31.65.100, okay? And a subnet mask of 255.255.224.0. All right, so right away, we know a couple of things, okay? What's the network ID? Well, I don't know the whole network ID, but I know at least it's going to be 172.31, right? because it's blocking those entire octets. I don't know what the third octet is because that's not shielding the whole thing. You can't, I mean, you might get good enough to binary to be able to do that in your head, but you can't just look at that and say, oh, that means the network ID, because it's only shielding like 3 bits out of 8. So let's deal with what we know first. We know it's 172.31.something.0. I know it's 0 in the last because the subnet mask has completely stopped, okay? So I do at least know that. Me personally now, I'm not going to deal with those at all, okay? I'm not going to deal with those numbers. I'm just going to deal with these two. And I'm going to take those two numbers and I'm going to convert them into binary. So let's start with 65. Okay, so that's the 0 in the 128, 1 in the 64-bit. And then it's going to be a bunch of zeros until we get to the last one, right? 64 plus 1 is going to be 65. So that's 65. Now, what's 224? Well, 224 is 128 plus 64, that's 192, plus 32, that's 224, okay? And you'll get used to seeing these. So there's your subnet mask. Now, if I AND those two values, I combine them, what am I going to get? Well, the first number is going to be a 0, 0 and 1. The second one is 1, 1. That's going to be a 1. Then I'm going to have a 0. Now, see, here's the deal. Right there is my line in this third octet. So it actually doesn't include that 1 bit because everything to the right of this mask is going to be the network portion. Now, even if we don't worry about that and we just continue this process of ANDing, we're going to get all zeros. And what is that number? Well, that number is 64. And guess what we just found out? We just found out that the network ID for this is 64. But you can see what I mean. You can't just look at those in decimal form and necessarily know that. Again, that one, in the grand scheme of things, that one was an easier one that probably could have been figured out in your head. But we have to get much further before we're going to be able to do that. So when you're dealing with custom subnet mask, that is masks that don't end on the decimal points, what we need to do is we need to just concern ourselves with that 1 octet. That 1 octet that is not where the mask is not on for the entire thing. We convert that number in the IP address to binary. We convert the subnet mask to binary. And then we can do this ANDing process. And we can figure out, exactly what that network ID is, okay? And there are other ways. We'll deal with some of the cheats, I think. There's a little cheat that I like to use, but we'll deal with that when we start talking about subnetting. So that's going to complete this demonstration. I just want to look at how the binary addresses, the binary subnet mask helped differentiate between the network ID and the host portion. We want to look at how that works with custom mask and the ANDing process. Always remember the calculator has that ability to very quickly check yourself, okay? But because you don't have the calculator on the exam, you're going to want to know how to do this manually. In this demonstration, we're going to look at how to configure IP addresses or just view an IP configuration. You can use the command prompt or you can use PowerShell, either or. I'll just open up my PowerShell window that I've got. The primary tool that you'll use to view an IP configuration is ipconfig. That's at least on a Windows machine. On a Linux box, Apple, it would be ifconfig. But ipconfig is going to show you your IPv4 address, your subnet mask, and then your default gateway. Typically, your default gateway will be the first available address on your network segment. Okay, so in this case, my network segment is 172.20.0, right? Because the subnet mask is blocking the first 3 octets. So 172.20.0, that matches this, and then it's the first available address of 1. Now, don't hold me to that because I'm just saying typically. It could also be the last available address, which would be 254 in this case. But a lot of times it is the first one. The real key for the IP configuration is to make sure that that matches that. Because my default gateway is my way off of my local network segment. So Remember, computers don't actually have the ability to send to other systems on remote networks, not without being told how to go about doing it. And so the default setting is, well, you just get configured with a default gateway. And I'm going to just throw a quick route print in here just to see my default gateway then populates what's called the they must just not have it labeled. They used to have it labeled as a default route. So the default gateway just populates what's called the default route, and it just says, okay, you're going to always send. If you don't know the answer, if you don't know where it's going, you send it to your gateway. So your gateway is your way off your local network segment. Therefore, your gateway has to be on your local network segment. Now, ipconfig does have a couple parameters like ipconfig all that can be used to show you a description of the NIC, whether it's DHCP enabled, the physical MAC address, DHCP servers, DNS servers, etc. We'll talk about those things when we go through troubleshooting. Okay. There are PowerShell commands. So far, the CompTIA is not really getting into this, but getNet IP address is a quick way of viewing the IP addresses that you have. Okay, so there's that. You've also got getNet IP configuration. Microsoft didn't do a great job on this. GetNet IP configuration is about as close as you get to ipconfig. When I say they didn't do a good job, is I can just hit ipconfig all and I can get all this information. With PowerShell, I need 2 or 3 different commands to be able to obtain that same information. So they didn't, I think they could have done a slightly better job. But ipconfig is the one that the exam will ask about. Now, the other way of checking that would be to go into, PC settings, into your network and internet, and just go into the properties of this. Of course, they've changed all of this. Changed all of this in Windows 11. It looks a little different. We're basically just trying to get into the network connections, which just took me into that. But you can go to Advanced Network Settings, and it'll show you these adapters. Okay. And then basically, here I can just see information about the adapter and its display. So I guess I should have probably had Windows 10 here, because you can go to the properties, TCP IP properties, and you can configure the IP address. But this demo is really just to view the IP configuration. ipconfig from a command prompt is going to be your best way of doing that. With IP addresses, we have a couple different categories of addresses, and the first distinction is private versus public. And this is going to be pretty straightforward. I mean, a private address is one that uses a reserved range and can't be used out on the internet. A public address is actually issued out by an ISP, and they're centrally managed and regulated, so that you can't just choose whatever you want, right? You have to actually get assigned a public IP address, and you can communicate directly to the internet. And then there are differences in flexibility. The Classful system is really, really old, up to, probably hasn't actually been used by ISPs in probably 20 years. However, we still just go by this. Okay, so we'll discuss the difference between the two, Classful and classless. Essentially, the biggest difference is Classful is less flexible in that the subnet masks have to stop on the decimal points. It defines classes of addresses, and it doesn't allow you to divide them up, and so it's extremely wasteful, whereas classless treats it like it's actually a 32-bit binary number, which it is, and allows us to have a lot more flexibility. Before we get back to that, because that can be a bit of a confusing statement, let's talk about our private versus public. So we said private or non-routable on the internet. They can be locally assigned within the organization, and they don't require us to purchase IP addresses. They just simply require us to use one of the reserved ranges for local area networks. Now that does give you some privacy, some protection from the internet, because you're using only a private address. But in reality, I mean, that's certainly not going to be enough, because if you could only use private addresses when you didn't need access to the internet, well, then nobody would use private addresses. The reason that we're still using IPv4 as much as we are is because of private addresses and something like network address translation. Okay, so private addresses are behind a device like a router or a firewall that's performing NAT, network address translation, meaning it's got a public IP address. So the client requests something from Google's web server, and that device changes the source IP address in the Ethernet packet to its own public IP and goes out to the internet essentially on behalf of the client, obtains the information for them. When the information comes back to the router, it swaps the IPs again and it sends it back to the original requesting computer. So it allows companies of, hundreds of internal machines can share a single public IP address. That's why 99% of the time when you sit down to a computer in a business, you're going to see an address that's either in the 10 dot, the 172.16 to 31, or the 192.168 ranges, because those are the predefined ranges that are reserved for private addressing. There is a fourth. It was reserved by Microsoft. That's 169.254.0.0 for the automatic private IP addressing. This could be seen as an alternative to DHCP, but that's not how it's utilized. It's technically just utilized as a troubleshooting mechanism, right? And I'll go through this again when we talk about troubleshooting. But if you ever see a 169.254, you've found the issue. Okay, this machine was trying to obtain an IP address automatically, and it couldn't. And after 30 seconds, it just generated its own. But it's not routable, doesn't work on the internet. It's pretty useless other than pointing out where the issue is. Public addresses, on the other hand, are required for hosts that communicate directly with the internet. They are routable and unique throughout the entire internet, and they are assigned by that central governing body, IANA, and then purchased through other service providers. So typically your ISP would be the one who's giving you a single IP address or a block of eight IP addresses or something, depending on your particular need. So individual client computers don't utilize public addresses. It is possible if you're at home on a cable modem or something that you might see a public address. Okay, that is possible. But the vast majority of the time we're using private ranges. Okay, because we're using private ranges, and all that means is that there's something between me and the internet that's going to translate and use its own public IP to go get me that information. So the original TCP/IP was assigned public addresses using classes. So it's called the classful system, and the class of the address also determined the default subnet mask, and therefore determined the number of networks and hosts that were available. Right? The subnet mask is the differentiation between network ID and host ID. So if that's defined, well then I know, okay, within this set of bits, we'll use Class A. Class A has a subnet mask of 255.0.0.0, so it only specifies the first octet as being available for network IDs. Well, that only gives you 127 possible networks, but you've got 3 octets worth of host IDs, and I'll show you how to figure this out later mathematically, but that gives you 16 million some odd. It's more than 16, a little bit more than 16 million. Class B, your first number is between 128 and 191. So that specifies a 255.255.0.0 subnet mask, and that gives you, 16,384 networks, 65,534 available hosts. Class C, 192 to 223, 2 million some odd networks, but only 254 hosts per network. Class D was for multicasting, and Class E was reserved for future use, but this whole classful system was scrapped because it was incredibly wasteful. It was incredibly wasteful, but as I said before, a lot of us, myself included, will still get honed in because Windows still does it. If you type 192.168.1.100 into your network config and then hit tab into the subnet mask field, it'll fill it in with the default Class C subnet mask because that's a Class C address. So it's just ingrained, and it probably will always be, that by default we're often looking at the first number and saying that's Class A, Class B, Class C to know what we're starting with from a subnet mask perspective. Just realize these days the subnet masks do not have to stop on the decimal points. Therefore, there can be other values, and we'll get into that. So that's actually called classless addressing. Classless addressing allows us to have variable length subnet masking, which gives us a lot greater flexibility and much more efficient use of the address space for IPv4. With classless, there technically are no default subnet mask, even though you'll catch many of us, acting like there are still. Subnet mask, the biggest key, as I said before, is subnet masks don't have to stop on the decimal points. And so they can be other things. I mean, technically, if a subnet mask stops on the decimal point, it's either 8-bit, 16-bit, or 24-bit, right? Either just the first octet, the first two, or the first three. With classless, they don't have to, it can be any of those plus more. And we also see it written in a different way. Classless interdomain routing, or CIDR, CIDR notation, writes the address and then slash and a number. So 192.168.1.250/24. What's the 24 mean? It means there's 24 bits in the subnet mask that are set to 1. Okay. If you want to convert that back out, that's going to be 255.255.255.0. Next one, /16. That means there's only 2 octets. So that's your 255.255.00. So see, even though it stopped on the decimal point, we're basically just writing it in a different way, a simpler fashion, as opposed to writing out the whole subnet mask. Now, the last one is an example of where you can get a little weird. /29. Well, whoa, what is that? Well, the decimal equivalent to that would be 255.255.255.248. Okay, and you can check me on that later if you want, but it's .248. So when you look at that, and you're like, whoa. Well, that means the vast majority of the 32-bit address, 29 out of 32 bits, are representing the network ID, which gives you a whole lot less to play with over on the host ID, only 3 bits. There's only going to be like 6 possible addresses in that subnet. But that gets done sometimes, because sometimes we have subnets that are simply router A to router B. There are no hosts. We don't need that many addresses. So anyway, I'm probably getting too far right now. Just think about the notation. So if they give you an address and they ask what class is this, then you need to be able to recognize the class based on the first number. But that's really a way old type of question. The better question is, here's this address /18. What's the subnet mask? And in order to do that, we'll just have to take and convert those numbers from binary to decimal. In this demonstration, we're going to be looking at CIDR notation. Sometimes it's just pronounced CIDR, but it really just, as we said, represents the different way of writing the subnet mask. Now, this goes along with classless addressing, and that's just because classless addressing doesn't really specify default subnet mask, but what you'll find is that depending on where you're looking, things are still represented in a classful way. When by that I mean they're written as, the IP address 192.168.100 and like that. And so obviously ipconfig is one of those places, right? Using PowerShell, you still are going to see that kind of notation. That is a classful notation. However, when you get into routers, when you get into firewall rules, packet filters, things like that, many times you're not referencing the subnet mask except for using CIDR notation, okay? And I'm not going to pull it up to show you, but for instance, on an Exchange Online server in Office 365, if we're creating a connector that tells it accept messages from these IPs, then we've got the option of doing a network range with CIDR notation or an individual IP address with CIDR notation. Same thing with firewalls, okay? So you're going to have those options, and we have to know that. Now, this is not overly difficult. Remember, each one of these is 8 bits, okay? And so to write that address, we would just write 1.100/24. And there's 32-bit total bits in a subnet mask, and all you're saying is that 24 of those bits are set to 1. That's it. That's all CIDR notation is. If you see something like that and they ask you what the subnet mask is, then you just have to type out 24 binary, or write out 24 binary ones and then 8 binary zeros and then convert it. Okay, but I'm telling you, if it's /8, that's going to be equal to 255.0.0. If it's /16, that's going to be equal to 255.0.0. And if it's /24, that's going to be, if it's /24, that's going to be your 3255s, okay? So save yourself some time. In other words, it looks like I deleted the 8 there, /8. Save yourself some time if it's one of those and don't bother. Well, what if it's something else, right? What if it is 192, 168.60.241/29, okay? What if you see something like that? Well, again, save yourself some time. I mean, basically, you're saying that all but 3 bits out of the 32 bits are set to 1. Okay, so we know then it's going to be at least 24. That's 24. And then you can just count out 5 more. 1, 2, 3, 4, 5. 3 zeros. Okay, that's your 32 bits. Then all we have to do is take that number and convert it back to decimal. Okay, in order to figure out what that's going to be. Well, what is that? 128 plus 64. 192 plus 32 is 224, plus 16 is 240, plus 8 is 248. They might ask you in the reverse, all right? Let's say write this, let's say 172.30.150.151/19. And they ask you, or I'm sorry, I messed that up. But anyway, then they say 255.255.224.0. And they ask you to write it in CIDR notation. Okay, well, again, that's 8 bits. That's 8 bits. So all I'm dealing with is this last one. 224 is in binary if you need to. 1, 2, 3, that's 224. Okay, how many bits? 3. In this part, you'll get to know and recognize, just be able to do that in your head. Because with subnet mask, you've only got so many possible values. There's the 128, there's 192, there's 224, there's 240, 248, 252, 254, 255. That's it. So that right there, 16 plus 3, that's your 19. And so if they ask what the CIDR notation is, write out the subnet mask, count the number of ones, and then say that's a /19 subnet mask, okay? So again, that's how CIDR notation is going to work, and it's a mix and a match in real life. Sometimes you see it in CIDR notation, sometimes you see it in the more standard classful notation, but we definitely need to know both. Now, in some networks, you actually do need to create what are called subnets or subnetworks. Okay, so we can get a single address that refers to an entire location, but we might have routers or layer 3 switches that are doing VLANs that require separate network IDs for each one of these individual segments. And so in those cases, we are subnetting. And with subnetting, what we're essentially doing is we're manipulating the subnet mask so that we can create unique network IDs. And that's easy to say. It's not easy to conceptualize until you see it. The key, though, here is that subnets are used to define interface connections in larger local area networks or wide area networks. The routers can be used to restrict or control traffic, but it definitely increases network performance because you have physically separate segments. You're not tying up the whole network with every packet. We're physically dividing servers, workstations, maybe voice over IP networks, things like that. But each interface and each segment is going to require a unique ID. So sometimes what we will do, and that's what they've done here, is we've started with a subnet there for the PC 172.23.1.0/26. Okay, 26 would be what? A 255.255.255.192. Okay, that's 2 more bits. the 128 and the 64. So then you see subnet 1 is 1.0. Subnet 2 is, looks like 0.0. Then we got a 2.0 over there. We got a 3.0, 4.0. You got all kinds of stuff. The graphic is probably more confusing than it needs to be because they're kind of shifting between networks. But we'll make sense of this. All subnetting is taking one network ID and making multiple unique network IDs out of it. So simple subnetting can occur, but complex subnetting can happen as well. Most companies use internal addresses. That's going to simplify the process of subnetting. Okay, so if I choose 10, for instance, well, I mean, basically, my network has between 10.0.0.1 and 10.255.255.254. That's a ton of host, right? It's 16 million hosts. So it stands to reason that I could take some of that's used for host IDs and I could use it for unique network IDs. And so that's if you're using internal, you don't have to worry about it being registered or anything. It makes it very easy to do. You can actually create fairly large subnets and still keep your subnet mask simplified. I call it simplified if it stops on the decimal. So you could say in this case, well, small subnets are going to use a Class C style addressing. Larger subnets going to use Class A, Class B. We're always using classless protocols and CIDR, but we can just come up with whatever makes sense for our environment. That would be simple subnetting if the masks stop at the decimal point. Complex subnetting is going to take us a step further than that, because in organizations that have a large number of internet accessible computers, you might need to divide a single address space into multiple sections. The way that we're doing this is by manipulating the subnet mask. The subnet mask right now tells me that the first 2 octets are the network and the second 2 octets are the host. What if I add some ones to the subnet mask? Okay, well, all of a sudden you move the line. We've looked at the ANDing process and CIDR, right? As soon as you add ones to the subnet mask, then you're moving that line that distinguishes between the network and the host. And that's one way of saying it. You're manipulating it. Another one is I'm borrowing bits from the host portion. And we'll talk about this as we kind of lay it out for you. We need to remember that IP addresses like subnet mask are binary numbers. So even though we look at them in dotted decimal notation, they're binary numbers. And in the subnet mask case, all we do is flip some zeros to ones, and we will have created ourselves some subnets. All right, in this demonstration, we're going to look at the process of creating subnets. We'll direct you to some online resources. If you would like, you don't certainly have to do this, but learn2subnet.com. Oh, actually, that might not be out there anymore. Let's go to Google, learn2subnet. They might have just changed it. Okay, how to subnet. Anyway, and this is one of many. I'm simply submitting this to you because sometimes it takes more than one explanation of this, all right? And you are not alone. I believe it was maybe the 3rd time that I'd heard this by the 3rd different person that it finally clicked, okay? So there are resources out there for you to work through. Subnetting.net would be one of them. Learn TCP/IP used to be one. Let's check that one. Maybe not net. Well, subnetting.net is definitely one, and that looks good. And these other ones probably just got taken down. So you can, like I said, I'm just looking for resources that would not be courses and whatnot, but basically just trying to get some more information. So subnetting.net, that's probably the best one. That looked really good. The process of subnetting is necessary when you have routers, okay? A lot of organizations, a lot of business networks are only going to just have one router. So they only have one subnet internally. No need for more, especially with smaller organizations. But then you get even small to medium to large size organizations that have the need for separate network segments. Now we're going to talk about network devices in the next chapter. So typically when we say network segment, I am talking about routers. However, layer 3 switches and VLANs can have the same concept. Okay, they're logical networks. They're not physically separated as they would be with a router. They're logical networks, but they still function the same. You're creating separate subnetworks. All right, now there's an easy way to do this and a hard way to do this. Remember, we're using private addresses. Okay, so let's say I've got the need for 4 subnets. Okay, I want to have a server's subnet. I want to have a DMZ, demilitarized zone, or now they like to call that a screened subnet. Most of us still call it a DMZ. That would be where internet resources are. A client's subnet and a voice subnet. Okay, so that's just an example. These would be pretty common. I want my voice data separated. I want the servers on one subnet. I want the clients on one subnet, and then I want a DMZ for internet accessible resources. Why would I do that? Well, security is the main reason, but you can also segment just from a traffic standpoint as well. But with routers or switches, you can control the traffic that is flowing between these different subnets. Okay, so that's an example of a time where I might need 3 subnets. Now let's say the organization has used the 10 dot address range. Okay, that's a private range. Well, that's a private range that provides you with, you remember how many possible IP addresses? 16 some odd million IP addresses available on a single network segment. And so because of that, you've got lots of options here. All right. Now, I personally would keep it simple. I would say, okay, the default subnet mask is that. I know we're not using a classful system, but that's still, what we're considering the default subnet mask for a 10 dot network. What happens? Why don't we just make the subnet mask? Why don't we just take this and add an octet? Okay. So what are we saying there? Well, we're saying, okay, it was just that. That was just one network ID. But did we just provide ourselves with additional network IDs? You bet we did. In fact, we went 8 bits. So we can use that entire octet and we can come up with whatever we want. I see this all the time where we'll have 10.1.0.0. That's one network. Then we'll have 10.2.0.0 or 10.10. It doesn't matter what that second number is. Those are all considered different networks so long as you use that 16-bit subnet mask. That's simple subnetting. That's just saying, okay, we want to keep the subnet mask stopping on the decimal points because it prevents you and I from having to go to the binary. All right. So simple subnetting just says we're going to take a network ID and the default subnet mask, and we are going to extend the subnet mask. Okay. Let me go over here real quick. Okay. So that 255.0.0.0 looks like that. In binary, all right? That is this, okay? So that's this. So all I'm saying is right now the subnet mask stops at that decimal point, and I want it to stop at this decimal point. So what am I going to do? I'm going to turn all of those bits on in the mask. I'm going to extend the mask. Another way of saying is I'm going to extend the mask and therefore borrow bits, these bits, that were formerly a part of the host portion of the address, and now I'm making them part of the network portion of the address. Now, sometimes people will get a little fancy here, and they'll say, okay, this is typically Cisco. They'll say that's the net ID, and then this is the subnet ID. And then you've got host. Okay. All they're really saying is everybody here, all the networks are going to share that same value, right? 10, 10, 10, 10. The subnet ID is what's going to make it different. I'm not trying to overly complicate things, but when you get into some of the Cisco stuff, they will use those terms. And it makes sense. You're extending the network ID, and the portion that you extended it for, that's what you can use as a subnet ID. And then we would just assign this one to servers. Doesn't matter which one. This one to clients. This one goes to the DMZ. And this one goes to voice. Okay? And then you go and assign those to router interfaces or to VLANs on a switch, and you're off and running. Right? Now, that's what we would call simple subnetting. The more complex subnetting is when you are dealing with this when you're not stopping on the decimal points. Okay? And so I'm going to show you a situation. Let's say, maintenance. Let's say, well, actually, we'll do the SAN subnet. And then a guest subnet. Okay, so let's say we've come up with a situation where we need 6 subnets. And what they're for is not really important. You'll get questions potentially that say, okay, here's your network ID. You need to create 6 subnets. How are you going to do that? So let's start out with 172.16.100 or 10.10. Okay, the very first thing you need to do is treat it like a classful address and write down the default subnet mask. All right, because right away that shows you that we're dealing with an IP address here, right? The mask doesn't cover those last 2 octets. We don't want to try this with an IP address. We need the actual network ID. So there's my actual network ID with a 16-bit mask. Now, we need to extend that 16-bit mask far enough to give me the possibility of having 6 subnets. All right, there's a formula for doing this, and the formula is 2, we'll get the calculator here. It's 2 to the, I guess those are my notepads. I thought that, does that not look like a calculator? It looks like a calculator to me. I'm still getting used to Windows 11 here. All right, so we're going to open up the calculator. We're going to put it in scientific because it's going to allow me to say, something to the power of, and it's this, okay? So the formula is 2 to the power of X. And X is the number of bits in the subnet mask that you have extended. So right now we're at 16, okay? So I'm just going to say, let's take it and let's add 3 bits. And so if we go 2 to the power of 3, we're going to get 8, right? That's not 2 times 3, that's 2 times 2 times 2. 2 to the power of 3 gives you 8. So if I extend the subnet mask 3 bits, that's going to give me 8 subnets, and we'll explain how that's possible. You might say, well, that's more than I need, so what happens if we only extend it 2? Well, 2 to the power of 2 is only going to be 4. You may create more subnets than you need, but that's not a bad thing because it's just you can have some in the future. All right, so we started out with 172.16.0.0 with a 16-bit mask. We're saying if we extend the subnet mask 3 more bits, then we're going to have the possibility of 8 subnets. Now, I want to show you something here. Okay, 3 more bits is a subnet mask that looks like that, right? Or 224, okay? And you can take and you can say, okay, does that really, how in the world does 3 bits give you 8 possible subnets? Well, basically all you do is, okay, well, let's see, how many possible values can I have in 3 bits? Okay, 0, 0, 0, that's 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. I always miss 1. That's 7 right there. Okay. Oh, and 0, 1, 1. That's the one I'm missing. Okay, those are all the possible values. There you go, 3 bits, and those are the possible values of those 3 bits. We have actually created 8 unique combinations of zeros and ones just by adding 3 bits. All right, I hope that makes sense. All you're doing is taking the default subnet mask and you're extending it. I jumped to 19 to save us some time. Let's just say you extend it to 1 bit. Okay, I'll get rid of this, but that just shows you can actually validate that there are that many number combinations. So you add 1 to it, which in decimal form would be like that, right? You add 1 to it. You say, okay, well, 2 to the first, that only gives you 2 subnets. All right, so I have to add a second one to it. That would put this at 192, but that's 2 to the second power. That's 4. That's still not enough. And so then we got to go 9, or we've got to go a third bit. So that's 224. And that subnet mask would give you 8 possible subnets. Okay. All right. So, and that might be all they ask in the question. They might just ask, okay, given this, what length of subnet mask would you need in order to do this? But sometimes they'll ask, other things like the actual network, because the next question is, okay, great. You just said if I extend the mask to 255.255.224.0, then I'm going to create these 6 or 8 extra subnets. Well, you actually have to have values for these subnets. So what are the subnets? Well, we could go like this: 172.16.0. But I'm going to do this in binary, okay? We're going to go 0, 0, 0. We'll leave the last one at 0, okay? 172.16. Remember, it's just the first 3 bits here that are covered up, right? This is 224, 111, 0, 0, 0, 0, 0. So it's just the first 3 bits. So let's just start plugging in our numbers like that. 0, 1, 0, 0, 0, 0, 0. 1, 0, 0. Okay, 172.16.110. Follow me? 172.16. Dot, I guess I forgot the 011 again. But you see what I'm doing? We're just manipulating those 3 bits. Those are your possible values. Those are the possible subnets that you have created. And again, I think I might be missing one, but you get the idea. That's one way of doing it. That's not the easiest way of doing it. I'm just trying to show you that, it's really just that part. It's that little subnet ID. How did we create that subnet ID? By adding 3 bits to the subnet mask. That's how we did it. It's not magic. This is all just the same math. Okay, but I'm just trying to show you kind of how that looks. Well, all right. So if that's not the easy way to do it, what's the easy way to do it? The easiest way the easier way is going to be to utilize this number. Okay, this is a little bit of a trick. What we're actually trying to do is we're trying to figure out what the delta number is. Okay, because we've established that using that subnet mask, I'm just going to put that here. So extending the mask from 255.255.0.0 to 255.255.224.0 or /19, that's going to give me those 3 extra bits for this subnet ID, right? Only in this case, it's going to be net ID, subnet ID, plus host, dot host. Okay, so the third octet is going to be, some of it is the subnet ID, the rest is the host. Don't worry about that. But what we're trying to figure out is what are the numbers? Well, technically, you could just go like this: 0, 0, 0, that's the first one. 0, 0, 1, that's the second one. 0, 1, 0, that's the third one. 0, 1, 1 is the fourth, probably. 1, 0, 0. You could do that, and you could just come up with all of them. But there's an E, and then convert those. Remember, those are just the first 3 binary bits. That's the 128, the 64, and the 32 bit. Okay, this is the one where we have to realize we're just dealing with those first 3 bits, and they have a corresponding value. Okay, there's an easier way of doing it. There's 256 possible values. You take the subnet mask that you end up with, and you subtract it from 256. That's going to give you 32. 32 is your delta number. Okay, your first subnet is going to be all zeros. Your second subnet is going to increase by the value of the delta. Your third subnet is going to increase again by the value of the delta. Your fourth, again by the value of the delta. Okay, so basically the reason that that's a real fast way is because all you need to do is figure out what the subnet mask is. What subnet mask, using that formula of 2 to the x, I haven't written that down anywhere here because it'll just look like I'm writing 2 times, okay? 2 to the power of x equals the number of subnets, where the x is the number of bits you've added to the subnet mask. So as soon as you've got that number and have it converted back into binary, or to decimal, subtract that number from 256, that'll give you your delta. Write out your network ID, and then in the third section, you start with 0 for the subnet ID, and then you just increase by the value of the delta. And you can keep going. Okay, you can keep going for as long as you need to go, but there will actually be a stopping point. And that stopping point will actually be, voila, the same number as the subnet mask. Okay, so, and there you go. Those are your 8 values. Now this part can get a little tricky. Let me get this, because you may be looking for the range of addresses. Well, the range of addresses in the first one is all zeros except for a 1 at the very end in the host portion. Okay, the last one, this is where this gets a little bit tricky, but it's going to be all 1s in the host portion plus a 0 at the very end. Okay, and so we would go like that. Okay, it's going to go all the way up to the next number, so that will always be 1 less, and then this can't be 255. It's going to be 254. So you're always going to go back. If you actually convert these 2 numbers to binary, which we won't do now for time's sake, but if you convert those 2, you'll see that this one is, as soon as the mask stops, it's all zeros and a 1 at the end. And then this one, as soon as the mask stops, it's all 1s with a 0 at the end. All right, but you get a little bit better at doing that. So that's the trickier subnetting. That's the subnetting that doesn't stop on the decimal points. That you need to use this formula to figure out first how many subnets and then what the corresponding subnet mask is. Then you use that subnet mask, subtract it from 256 to figure out your delta number. Then you write out your networks. Then you can write out your available address ranges in those networks. All right. Again, having said that, don't worry if that all still sounds like it's a different language. I've tried and have explained this for years and years and years, so I try to do a good job, but I completely understand, because I myself, as I said, had to hear 2 or 3 different takes. So maybe go to that subnetting.net, watch through this video again, do some of these exercises on your own. We'll obviously have some questions as well at the end of the chapter for you to kind of validate this knowledge. But hopefully that's helpful to you. This is definitely something that is going to be important. They won't ask you about the whole process, but they ask you about different steps within the subnetting process.